Hello everyone. In this review, we're going to talk about nomenclature, so naming things. And I cannot stress to you enough how important this is going forward. We did a lot of practice for it before we left for the break. If you were still struggling, then this is definitely going to be something good for you. Even if you were fine before we left to the break, you still need to go through and practice and review this. I'm going to go through and kind of hit all the high points for everything. If you feel like you're comfortable, fast forward all the way to the end where I have some practice and try and do those things by yourself. You can always do things on here by yourself. You can pause, unpause, try it, then you listen to my explanation. Also, if you're watching on YouTube, you can also set it to 2 times fast forward. So if you just need like a real brief review, set it on 2 times fast forward and go ahead and get through it. First, we are going to talk about naming ionic compounds. And naming ionic compounds is different depending on whether you're a main group element or whether you're a transition element. And more so, main group metal or transition metal. So just a reminder of what main group metals are. That's going to be our group 1s, our group 2s, and in this case, it's also going to include aluminum. So with ionic compounds, remember that an ionic compound is formed between ions of opposite charges. So it's formed between a cation and an anion. So something that's positively charged and something that's negatively charged. When we talk about naming, the first name is going to be the name of the cation, and the second name is going to be the name of the anion, except where we change that ending to IDE. So for instance, the first one, we have Na and Cl. So Na, that's sodium, and Cl, that's going to be chlorine. So instead of writing sodium chlorine, we change the ending of that name to IDE. So that would be sodium chloride. For the second one, it's going to Mg is magnesium. And then O is, of course, oxygen. So we're going to change oxygen to oxide. Then we have sodium 2S, so Na2S is what we have. So sodium, or Na is of course sodium, and S is sulfur. So we're going to change sulfur, change the ending to IDE, so that would be sulfide. So our name for Na2S is going to be sodium sulfide. In this case, you don't really have to worry about these subscripts because the name implies how many is supposed to be there. And the reason why this is Na2S instead of just NaS is because sodium is going to have that +1 charge that it likes to have, whereas sulfur, or in this case sulfide, has that -2 charge. Well, in an ionic compound, we have to make sure that these charges balance out. So the reason why there's 2 sodiums there is because there needs to be those 2 positives to balance out the 2 negatives. Now when we transition from going from the name to the formula, so if we're given the name, how do we write out this formula? And it all goes back to balancing the charges. So rubidium, if we find that on the periodic table, rubidium, that's Rb, that's in group 1, it's going to have a +1 charge. And just for some sort of accounting system, I always like to write the charge above the name. And we have chloride. Well, chloride or chlorine, that's going to have your -1 charge because it's in group 17. So if we have a +1 and a -1, those are going to cancel each other out, so this is going to be neutral. So in this case, we don't have to worry about adding atoms to balance charges. The charges is already balanced. So this is just going to be RbCl for rubidium chloride. Next, we have beryllium oxide. So on the periodic table, beryllium, it's in group 2. It has a +2 charge. Oxide, that has a -2 charge. So we can just write this as BeO. Our charges already balance out. Now in terms of calcium chloride, let's take a look at that. Calcium, again, he's going to be in group 2. He's going to favor the +2 cation. And chloride's going to be a -1 cation, or excuse me, a -1 anion. So a +2 and a -1, this doesn't offset, their charges don't offset. So in order to have this offset, we need to add another chlorine or another chloride. So if we add another one, now we're at a total of -2, and calcium has still, one of them has +2. So this is going to be CaCl2. And again, the reason why we have two chlorines is because we need both of these negative charges to offset the positive 2 of calcium. Now in this one, we're going to talk about naming ionic compounds with transition metals. And let's remember what our transition metal is, or metals are. They sit in between this group 3 through 12. These are going to be our transition metals. Now, we're not going to lose our base system of naming ionic compounds. What's still holding true is that the first name is the name of the cation, and the second name is the name of the anion changed to IDE. The difference between these transition metals and main group metals is with main group metals, things in group 1 and group 2, and then of course aluminum in group 3, they're all going to have the same cation. So they really don't have any variation in that. However, with transition metals, they can have many different cations depending on the compound that they're in. So for instance, iron can be iron 2, it could be +3 or +4. Manganese, he can have from +1 all the way to +7. So in order to indicate what charge each metal has, we're going to add a Roman numeral to it, the name. And that Roman numeral is going to sit in between the first name and what we call the second name. So for instance, we have CuO. Based on previous rules, we would call this copper oxide. However, because copper is a transition metal, it could be +1, +2, or even +3. So we need to indicate in this compound which cationic state it exactly is. So in order to do this, we really look towards the anion to help us with that. So in this case, oxygen. Oxygen's in group 16. He's going to typically be a -2. So we again have to make sure these charges balances out in these ionic compounds. So here we only have one copper as indicated by this formula. So the only way that this can, or these charges can balance out is if copper in this case is a +2. So here we would call this copper. And then again, we're adding the Roman numeral to indicate the charge. This Roman numeral has nothing to do with how many atoms are present. It's solely letting us know the charge of this cation. So this is going to be copper 2 oxide. Looking at the next one, we have Fe2Cl2. So Fe is of course iron, and it's going to be a transition metal here. So it can have numerous cationic states. So we're going to look again to the anion. So we have chlorine. Chlorine's a -1 because it's in group 17. So here we have two of them. All right, so that's 2 - 1. So we have a total of -2 here. Now we need to balance out that -2 with the irons. It also indicates that we have 2 irons. So we have to spread this -2 charge out over 2 different atoms. So in this case, each one of these irons has to be a +1. So this one would be named iron 1 oxide. Now say for instance, just kind of as a bonus, this is just FeCl2. Again, we're going to still have a total of -2 here. In this case, we only have one iron to help equalize out this charge. So in this case, this iron just needs to be a +2. So this would be called iron 2 oxide. For the next one, we have manganese and nitrogen. So in this case, it says we have 2 nitrogen. If I find nitrogen on the periodic table, that's in group 15, it's going to carry a -3 charge. And we have 2 of them. So now we're at a total of -6. Over here with manganese, it indicates that we have 3 of them. So with 3 of them, each of these has to equal a total of +6. So if you simply just say 3 into 6, that means each one of these is going to have a +2 charge. So we will call this manganese 2 nitride. Now when we go from a formula to, when we go from a name to a formula, again, we're just trying to make sure that charges balance here. The Roman numerals already tell us what the charge has to be. So again, I'm just going to write those over the respective name. So copper is a +1. and chloride, that's going to be a -1. Those balance out, so we can just write the element symbols. So that would be copper 1 chloride. With iron 2 oxide, this is going to be very similar. The charge on this iron is a +2, and the charge on oxygen is going to be a -2. So those charges balance each other out, so we can just write FeO. The last one, tin 4 nitride. So in this case, this tin is going to carry a +4 charge, and this nitride carries a -3 charge. A +4 and a -3 don't balance out, and so in the formula, we need to make sure to indicate the correct number of atoms that would help balance this out. So for this case, since we really can't get a 4 to a 3 or a 3 to a 4 very easily, what we're going to have to do is look at a number that they can both go into and try and take that the least number that we can. So for instance, kind of the least common multiple between 3 and 4 is going to be 12. So we need to get both of these to 12. So in order to get a -3 to a -12, we're actually going to need 4 of these nitrides. So if we have 4 nitrides, we have 4 N's, okay? 3 times 4, that gives us a total of -12. Now in tin is a +4. Well, in order to get to 12, we need 3 of these. So therefore, tin would be SN3 N4. Now we're going to switch over to naming covalent compounds. So remember that a covalent bond is formed between atoms that share electrons. So with the first name, that's still going to be our name of our element. The second name is going to be the name of our element changed with its ending to IDE. That's similar to what we just did with ionic compounds. Here where our difference comes in is that we have to indicate prefixes, or we have to use prefixes to indicate how many atoms there are. We didn't have to do that with ionic compounds because charges, we knew that their charges had to be balanced, and so that would dictate what type of numbers we would use when we were going from name to formula. But here, since we're not dealing with charges, we're going to have to use these prefixes to indicate their respective numbers. And so the prefixes we use, I'll just write them up here, are going to be mono, di, tri, tetra, penta, then we're moving on to 6, which is hexa, hepta, octa, nona, and deca. So those are going to be our prefixes that we use. So it's important to note that we always are going to want to use a prefix except mono on the first name. You never use mono if you're talking about the first name. Otherwise, you're always going to want to have a prefix. So for the first one, we have 1 carbon and we have 4 chlorines. So again, I'm looking at my prefixes. Well, I only have 1 carbon, so that's mono. But I just said we're never going to put mono on the first name. So for this one, this would just be carbon. And for chlorine, we're going to change that ending to IDE. I'm sure y'all can probably hear my cat. Sorry about that. But we have chlorine, and we know there's 4 of them. So 4 is going to be tetra. And then it's going to be chloride. So this one would be carbon tetrachloride. Next, NO2. This is going to be nitrogen. Again, we're not using a prefix because we don't use mono on the first one. And then here we have 2 oxygens. So that's going to be dioxide. Now, for instance, if this was just NO, okay, again, it's still going to be nitrogen. However, we do call this monoxide. So nitrogen monoxide. So we do use this prefix mono on the second element. That's completely fine. Also notice that I didn't write it as monooxide. So we really don't like using double vowels when we're naming these things. So anytime you run across these double values, what you're going to want to do is you're going to always drop the value, or not value, the vowel from the prefix. So always drop your vowel from the prefix. Next we have P4O10. So 4 is going to be tetra. So this would be tetraphosphorus. And then we have 10, so that's dec or deca. But here we have oxygen, which is oxide. So again, I don't want those double vowels there. So I drop the A from the prefix, and I just call this decoxide. Now let's go from the name to the formula. So carbon, there's no prefix here, so that indicates 1. So this is going to be carbon dioxide. There's 2 oxygens, so that's going to be CO2. Then we have diphosphorus pentasulfide. Di is 2, so it's going to be P2. Penta, that's like 5, like the pentagon, so S5, P2S5. Lastly, we have nitrogen trichloride. So nitrogen, there's no prefix, so it indicates 1. And then we have trichloride, so that's 3 chlorines. Polyatomic ions. Guys, remember, these are the compounds that are covalently bonded together, but they still have an overall charge. So because they have this overall charge, despite being covalently bonded together, they're going to end up forming ionic compounds when they combine with another cation or with another anion. So you have the list. Know them. This is the perfect opportunity to stay up on these. Remember, you need to know both the formula and the charge associated with them. Now we're switching gears a little bit and we're going to talk about naming acids. Remember, at this point, it's not really important that you understand what an acid is. We just need to be able to know how to name them. We will get to what an acid is later on in the course. So in this case, we're going to talk specifically about binary acids. And remember, binary, that just means 2. So yeah, 2 things. So binary acids typically have this formula where there's some element and it's bonded to a hydrogen atom. Also remember, with acids, we designate what an acid is by adding this parentheses AQ, and this just means aqueous solution. So whatever this is, it's in water. So for these, we're going to drop the prefix hydrogen, add the prefix hydro, we're going to change elements ending to ic, and we're going to add acid at the end. So for example, the first one, we have hydrogen and chlorine. So I'll write that out to the side. Hydrogen and chlorine. So we know this is an acid because it has AQ beside it. So we're going to drop hydrogen. Instead, we're going to have the prefix hydro. And we're going to change the ending of the non-hydrogen element to ic. So this would be hydrochloric. And then we're going to add acid at the end. So HCl is going to be hydrochloric acid. For our next one, this would be hydrofluoric acid. Now, if you come across this just as HF, notice this doesn't have an AQ beside it, so that's not an acid. So this would just be hydrogen fluoride. So it's important to remember about this AQ. So if we have the acid and we're trying to go to the formula, again, we're just trying to undo things. So we know this is an acid because it has acid in the name. We also know that this is a binary acid because we have the prefix hydro. So therefore, we know there's going to be an H. And bromic, that's just going to be bromine. And then we have hydroiodic acid. Again, we know that the prefix, there has to be a hydrogen because we have a hydro and we know it's an acid. So this would be hydroiodic or hydrogen and iodine. And when you write these out, when you're going from the name to the formula, I still would also include parentheses AQ. However, because we know it's an acid, because it's an acid, then you can just write HBr or HI. That should be fine also. Next, we have oxyacids. So oxyacids are going to be a hydrogen with some polyatomic anion. So for this, we're just going to drop hydrogen completely. When we talk about acids, especially oxyacids, hydrogen's understood, so we don't need to include it in the name. Then we're going to change the ending of the polyatomic ion. Depending whether it's an 8, we're going to change it to an ic, and then if it's an ite, we're going to change it to an ose. And then, of course, we're going to add acid at the end. So here I have HNO3. I know this is an acid because it has AQ beside it. So I don't have to worry about putting hydrogen at all in the name. That's completely understood. Now I have NO3. So the first thing I need to ask myself is, what polyatomic is this? Well, this is nitrate. So based on my rules, I have an 8. So I need to change it to ic. So instead of nitrate, this is going to be nitric. And then I add acid at the end. So this is nitric acid. For the next one, we have HNO2. This is nitrite. So an ite goes to an ose. So this would be nitrous acid. Now, in terms of if we have something like with a per or with a hypo, you're also going to want to retain that in the name. So, for instance, with our some of like hypochlorite. So if we have hypochlorite, in this case, if it's an acid form, then we have an ite to an us. So we would still retain this hypo part, and we would just call it hypochlorous acid. And the same thing with perchlorate. That would be perchloric acid. So make sure you're still retaining those prefixes if it has it on the polyatomic anions. So going from name to formula, for example, we're over here. If we have sulfurous acid, again, we're just going to undo this. So we know it ends in ose. So that means it originally came from an ite. So that would be sulfite. So sulfite is going to be SO3 2 minus. Okay. So in this case, we know what our anion is, or our polyatomic anion is. Now, so I'm going to go ahead and write that down. Okay. However, this is an acid. We know it has hydrogen with it. That's kind of understood in the name. Now I need to figure out how many hydrogens go with it. Well, here, that's dictated by the charge. So we have a -2. So if we have a -2, hydrogen is the +1 cation. I know I need 2 hydrogens to balance that out. So this would be H2SO3. Next, we have acetic acid. So with acetic acid, again, we're just trying to undo things here. So with it, we have ic. So we know this ic came from an 8. So this would be acetate. All right. And with acetate, that polyatomic ion is C2H3O2, and it has a minus charge. So I can go ahead and write my polyatomic anion up here. Now again, we need to figure out how many hydrogens go with it. Well, here we have a -1 charge. So to balance that out, I only need 1 hydrogen. So this is just going to be HC2H3O2. So that's how we would write this. On this slide and on the next slide, I have us practicing everything we've just covered. So this one's going to go from formula to name. On the next slide, it goes from name to formula. I've included the periodic table off to the side in case you need it. So I'm just going to get in and start doing this. Again, now's a great time to pause the video, get out a sheet of paper, try it by yourself, and then you can come back, fast forward to the end, and see what answers that I have. Or if you're not sure on some of them, you can also hear my explanations as well. So I'm just going to get right into it. So here we have nickel and sulfur. So I know this is an ionic compound because nickel is going to be a cation in this case. So nickel's also a transition metal. So because of that, I'm going to need to include Roman numerals with it. So in order to figure out what charge it has, I look to the anion. So sulfur is a -2. So if sulfur is a -2, I only have 1 nickel. So that's going to be a +2. So this is going to be nickel 2 sulfide. The next one, I have boron and chlorine. That's going to be a covalent compound. So with this is going to use the prefixes. So this is going to be boron trichloride. And remember, we never use mono with the first name of the element. So it's not monoboron, it's just boron. Next we have, I see magnesium. Magnesium is a +2 cation, so I'm not going to have to include Roman numerals here. I just can jump straight into no Roman numerals. And I also don't have to worry about the charges balancing in this case. Because the formula is already written, I know my charge is already balanced. So I just have to write the name. So this is going to be magnesium iodide. SO2, this is going to be a covalent compound. I don't see any charges. So I just need to indicate with prefixes. So sulfur dioxide. Number 5, sodium, that's a cation. All right, that's going to be a +1 charge. Now, I also know what you're thinking. In this case, it's like, well, hold on. Hydrogen's also a +1 cation because it's in group 1. That's not going to be the case when we talk about metal hydrides. And metal hydrides, that's anything where a metal is combined with hydrogen. So when hydrogen is combined with a metal, if you remember from our oxidation rules, this hydrogen is actually going to flip to a negative sign. All right, this hydrogen is actually going to flip to a negative sign. Regardless, guys, we're still using our same naming rules. That doesn't matter. So this is going to be named sodium, right? And then we have hydrogen. We drop the ending, add IDE. So this is just sodium hydride. Number 6, I look at this and I say, well, man, this is a lot of elements, okay? And most of the things that we've just learned how to name is a binary. So if you see a lot of elements, the big polyatomic sign should be going off in your head. So anytime we have polyatomics, we don't really change the name of them, unless, of course, they're in acids, then we're going to change the ending. So I just have to remember what polyatomics these are. Well, this is NH4. That's ammonium. Right? And then C2H3O2, that's acetate. So this is going to be ammonium acetate. Number 7, big hint right here. This is AQ. That means it has to be an acid. So we have two types of acids. We have binary acids and we have oxyacids. This is going to be an oxyacid because it has a polyatomic. Okay, so that's going to be your big indicator here, is that it's a polyatomic. So with polyatomics, we have to change the 8 to the ite, or excuse me, the 8 to the ic and the ite to the os. So for this one, we have to know that NO3 is nitrate. So if it's 8 goes to ic, and here we're not going to have to worry about indicating that there's a hydrogen. So this is going to be nitric acid. Number 8, I see copper. That's a transition metal. I know Roman numerals has to go with it. So here, oxygen's a -2 charge. I have 2 coppers to distribute that by. So those 2 coppers, each one of them has to be a +1 to balance out that -2. So this is going to be copper 1 oxide. And lastly, we have HF. Again, AQ, big indicator that this is an acid. There's only 2 elements here, so it's going to be a binary acid. So we're going to keep the prefix hydro. Then I have fluorine, but we're going to change the ene to an ic, and then add acid on the end. Last slide. This is going to be name to formula. So cobalt 3 oxide, that Roman numeral 3 indicates that this is a +3 charge. Oxygen's a -2. I need to be able to balance these out, and doing that, I got to find that least common multiple, which in this case is going to be 6. So I need to get both of these to 6. So that would be another +3, and then 2 more -2s. So altogether, I have 2 cobalts and 3 oxygens. So this would be CO2O3. Cesium, that's CS. Iodide, that's I. This is going to be a +1. That's a -1, so CSI. Those charges balance out. Nitrous acid. Os came from ite. So this is going to be nitrite. And nitrite is going to be NO2-. That's our formula for nitrite. So we have NO2. Again, this is going to have hydrogen with it because it's an acid. Here we just have a -1 charge, so we only need one hydrogen with it. So that would be HNO2AQ. Strontium carbonate. Carbonate's going to be our CO3 -2 charge. Strontium, Sr, it has a +2 charge. So here, these charges balance each other out. So we just need to write Sr, CO3. Lead 4 nitrite, that means this lead has a +4 charge. Nitrite, that's NO2 -1. So in order to balance these out, I'm going to need 3 more nitrites for a total of 4. So we have a -4 on this side. So this is going to be lead, Pb. I have to put this polyatomic in parentheses, and then we're going to have the number 4. Number 6, diphosphorus pentoxide. Okay, this is covalent because we see that it has these prefixes. So I just need to indicate the prefixes on each element. Phosphorus has 2, that's di. Oxygen, penta, that's 5. Hydrochloric acid, number 7. So it has the prefix hydro, so that means I know it's going to be a binary acid here. So with binary acids, they of course have this general formula, HX. So chloric, I know that came from chloride, so this is going to be HCl, and then if you would like to put AQ in parentheses, of course you also can. Number 8, sodium sulfite. So that's Na plus sulfide, sulfur, that's a -2. Here, in order to balance out the -2, I need one more sodium, so this is going to be Na2S. Lastly, we have nitrogen trioxide. Nitrogen doesn't have a prefix, so that's just 1. And then trioxide is going to be O3. So see how you did? Let me know how you did. If you need any clarifications, please let me know. Otherwise, I hope everyone has a great day.